Hello everyone. So we also have started discussion regarding fabrication techniques associated with sensors, and in the last lecture we have discussed different details associated with clean room, what is a clean room and what are the different parameters associated with clean room, and how how important a clean room is in microfabrication techniques. So it's very important that while you start a microfabrication technique, you do that inside a clean room, usually in most of the cases. But I also have mentioned there are different other techniques. For example, if you want to develop a flexible device or a printed device, there are different flexible fabrication technique or printed fabrication techniques which will be which are important in those cases. You can do those fabrication also inside a clean room, but in many cases without a clean room also you can develop different sensors. However, microfabrication technique is one of the standard technique. That's why it's better you learn more about microfabrication technique and clean rooms. I will also give you maybe a brief idea about other fabrication techniques as we go ahead. But today we will start the first process that I mentioned in the previous lecture, which is known as deposition. So deposition is a process. From the name itself, it is very clear that if you want to deposit one material on top of a substrate, we usually use different deposition techniques. So deposition can be divided in majorly in three different categories. The first one is physical vapor deposition, the second one is chemical vapor deposition, and then we have thermal oxidation. So thermal oxidation, one can argue whether it's a deposition technique or not, because in thermal oxidation we generally grow a material on top of a substrate rather than depositing it. But it's also a kind of fabrication technique, so I thought of keeping it in the deposition itself. But majorly we will focus on physical vapor deposition and chemical vapor deposition. Both these techniques are very popular in microfabrication techniques, and both these processes are widely used in different device fabrications. As I have said, thermal oxidation is a different process. So just to briefly mention you, thermal oxidation is a process through which you can develop, say, an oxide on top of a material. For example, if you have silicon and you want to grow silicon dioxide on top of it, you can use thermal oxidation process, where the silicon will be oxidized and the SiO2 layer will be grown on top of silicon. So it's like it will grow slowly on top of the substrate. Okay, but we will first discuss different physical vapor deposition techniques. So again, physical vapor deposition technique can be classified in different fabrication processes. So the first one is thermal evaporation. This is a kind of physical vapor deposition technique. Then you have e-beam evaporation, then you have ion plating, and you can also have a sputtering technique, which is a physical vapor deposition technique. Now each of these techniques are different, and based on your requirement you can decide which process to use for your fabrication. So the majorly, or I would say the most widely used PVDs are thermal evaporation, e-beam evaporation and sputtering. So we will limit our discussion in this course in these three. Okay, that thermal evaporation, e-beam evaporation and sputtering. Again, the sputtering technique can be of various types. It can be DC sputtering, it can be DC magnetron sputtering, or it can be RF sputtering. So that also can be classified in 2-3 different processes. That again we will briefly discuss once we discuss the sputtering. Okay, so this is more or less a brief summary of deposition techniques. So to give you a basic idea what physical vapor deposition technique mean, so there are various types I have said, but if we discuss the basic principle behind physical vapor deposition, then it is a technique where you have a certain material, and once you heat that material, it will create vapors, and these vapors will get deposited on a substrate, and that deposition will create a thin film over a substrate. So ultimate goal of this deposition technique is to create thin films over a substrate. Now, to give you an analogy, for example, say if you have a container and it has some water kept inside that container, then if you say apply heat, then the water will start evaporating. Now, when this water will evaporate, and if you keep another container on top, this evaporated water molecules will condense in that container, the container kept on the top, and then they will create, or they will get deposited on the top container. Now, based on different surface energy and etc., you will find they are forming different droplets. I am not going into that details, but what I want to say is, once they are evaporated and once they came in touch, or once they come in touch with the top container, then they condense and create a film over the top container. So, it is similar to that. Okay. Now, the order of thickness that one can achieve using physical vapor deposition can vary from 5 nanometer to 300 nanometers. And as I have said, that physical vapor deposition can be classified into majorly in three different processes. One is thermal evaporation, one is EVM evaporation, and the third one is sputtering. So, each of these has its own process associated with it, and all these three processes are kind of widely used in different device fabrication techniques. So, we will start with the thermal evaporation technique. Now, just to give you a bit more idea about how this physical vapor deposition looks like, we are not discussing the thermal or EVM at the moment. We are still into the basic details of PVD, physical vapor deposition. Now, this particular process is a kind of high vacuum process. So, what you have to do is, you have to create a chamber where you can apply high vacuum condition, and then you have to start the evaporation or the deposition process. That is why one can also call it vacuum deposition technique. So, deposition of ultra thin layer of pure material on a surface or substrate is the target. So, the target is to deposit a pure material on top of a say substrate. Then vacuum is necessary, as I have said, because the air molecule may otherwise react with the material under consideration and can contaminate the entire process. So, that is why high vacuum is necessary, because in the air we have different types of gases. Now, for example, say if you want to deposit aluminum on top of a substrate, the aluminum at high temperature may react with the oxygen of the air and may create Al2O3, that is aluminum oxide, and then the pure aluminum may not get deposited on the substrate. So, that is why vacuum is necessary. And then one also has to have a mechanism through which you can heat the material under consideration in order to create that evaporation process. So, you need a substrate, you need a vacuum chamber. Inside the vacuum chamber you create high vacuum, and then you also need a source which is say 99.999% pure, because you want to deposit a pure material on the substrate. That is why you also need a source which is highly pure, and then you need a heating technique. So, usually what you can do is, you can go for a resistive heating. Resistive heating meaning, if you have a resistor and if you pass current through it, then definitely that resistor will generate some certain sort of heat. We call it resistive heating. Why this heat will be generated? Because it's a function of the current passes through the resistor. So, it's like I square RT. So, based on that you can create a heat and can create a kind of environment where the source will be evaporated at high temperature, and then the same will be deposited on a substrate kept on top of that source material. So, this is basically the physical vapor deposition technique. So, let us discuss about thermal evaporation technique. So, whatever we have discussed, from there you now get to know that what are the different conditions that one has to maintain and what is the purpose of the deposition technique. Briefly saying, purpose is to deposit a high pure material, source material on a substrate. Now, in case of thermal evaporation technique, it uses heat for this purpose. The second thing is sufficient heat melts the source and forms gas, that is material starts evaporating. Then the gas touches the substrate and condenses to form the thin film, as we have discussed previously. Metal and dielectric both can be used in this process for deposition. Metals are mostly used in this case as the melting point of metals are comparatively low and also have steady deposition rates. So, these are the different key information associated with thermal evaporation. So, what we do is we take a small piece of pure material, or say mostly we use metal in this thermal evaporation technique, and then we put this in a container. We call this container a boat. Now, this is how it looks. Then you put the material here, then you place this boat and connect it with source, high current source, and then you pass current through the boat, and once current is passing through the boat, it generates heat and it melts this material kept. For example, say in this case we have taken gold. So, once the gold is heated and once it melts, it produces gas. Gas meaning it evaporates, and once it evaporates, it goes up, and if you keep a substrate on top, it will condense on that substrate and then it will create a film on that substrate. So, this is the typical process, and here I have listed the melting point of different materials. Now, from the discussion itself, it is very clear that your boat material should have a high melting point than your material under consideration, that you, or source material, right? Because if this boat material has a low melting point, then it will melt and will create contamination. In fact, it is not possible, it will melt RDL. So, that is why boats are usually made of tungsten. You can see in the list, tungsten has a fairly high melting point, and then you use different other materials in order to different other materials as source in order to create a thin film on a substrate. Then there is another very important thing inside the thermal evaporation or physical vapor deposition technique. This is known as crystal sensor, which monitors the thickness, because once you want to deposit a material on top of a substrate, you possibly would like to know what is the thickness of that material. Most of the time we decide that we need, say, 50 nanometer thick gold layer or 100 nanometer thick gold layer, and for that purpose you need a thickness monitor. So, thickness monitoring is not mandatory. If it is not there, then what you have to do is you have to optimize the process. So, you take the gold, you do a certain sort of deposition, you decide what should be the current, what should be the time, and then see what is the thickness. So, you again try with different current and time, and then you optimize what should be the current value, what should be the time, what should be the vacuum condition that can create a 50 nanometer thick layer on silicon. So, that is a kind of trial and error method, and through which you can decide what should be the recipe. Recipe means the process that one should follow, just like cooking. In cooking you have a recipe, you follow these processes in order to make, say, a certain dish. Similarly, in this case also you have to first decide the recipe. Once you decide the recipe, then you can follow that recipe in order to create the same sort of output or same sort of features. Okay. But if you have a crystal sensor inside, in situ, you can, while the deposition is going on, you can decide what is the, or you can monitor what is the thickness of that material on top of the substrate. Okay. So, there are various heating techniques available. The one that we have said is resistive heating. So, this is like a filament coil heating that is shown over here. So, you have an heated spiral, you have a source rod, you put this inside the filament, and then you can start the evaporation technique. So, it is a simple and inexpensive technique. It has a contamination risk because at high temperature you may find the coil material also is kind of evaporating, and that may create a contamination. So, this is one type of heating technique. Then we have inductive heating technique, where you have a container, this is a crucible, and then you put the source inside, and then you use inductive coil as it is shown over here. Then it creates an eddy current. So, that actually helps to create the evaporation. So, in this case also it is simple and inexpensive, and it also has certain sort of risk of contamination, because it has a crucible material, it has the inductive coil material. So, they also can starts evaporating at high temperature and can create certain sort of contamination on the film that you are creating. Then there is another technique which is E-beam heating, which is not a thermal deposition technique, it is an E-beam deposition technique, but briefly mentioning over here. In this case, what you do is you have an electron beam source, you focus the electron beam onto the source, and that electron beam once hits that source material, they create a lot of thermal heat, and that melts the material and creates the evaporation. So, in this case the risk of contamination is way less than that of these two techniques or thermal evaporation techniques. So, here we use a focused beam of electrons, and that locally heats the material, and this can be used to heat or evaporate high melting point materials as well. For example, in this case, there is a limitation as far as the temperature or temperature of the coil or temperature of the boat is concerned, but in this case you can reach a higher temperature, and that is why high melting point materials also can be deposited using this technique, but it is a separate technique, we will discuss it later. So, here again I am showing you what is the real time thickness monitoring, how it helps us in the process. So, in this case, for example, say this is the vacuum chamber, here is your substrate. For example, here you can consider silicon, say the source material is gold, you are using resistive heating. So, you are using a current through this, and now it is evaporating. Now, once it is evaporating, it will also evaporate and go there, it will also evaporate and will go to the substrate, it will also evaporate and will go to the thickness monitoring or crystal sensor, it will also hit the crystal sensor. In this case, the frequency of that crystal sensor will change as the deposition is increasing, because the mass is increasing. That is how a crystal sensor works. Now, based on that frequency, you can decide how much is the thickness on the crystal sensor. Similarly, similar thickness will also can be expected on the substrate. So, you kind of make an calibration, and then while the deposition is going on, you can decide that okay, this is the level of thickness that we already have achieved. So, here I have given you a kind of real image where the thickness monitors are shown. These are the thickness monitoring unit, crystal sensors, and then you have a substrate. So, that is how one can take advantage of a real time thickness monitoring unit. However, you should remember, because it is a thermal process. So, once you heat that material, and for example, say at 50 nanometer thickness you want to stop the process, say your crystal monitor said or crystal sensor said that 50 nanometer thickness has been reached, and then if you switch off this entire system, you may end up getting say 55 nanometer or 60 nanometer, because the moment you switch off the system, the heat will not go to normal temperature or to less, or it won't cool down so fast. So, there will be certain process will be there even if you switch off the system, because of that heat present in the system. What I mean by that is, say currently you have seen from the crystal monitor that 50 nanometer is achieved, you switched it off, but the source material is still heated. It may take 15 minutes, 20 minutes time to cool down. In that 15-20 minutes, the evaporation process will be still on, and that will create an extra layer on top of that 50 nanometer thickness film. So it may end up, you may end up getting a 55 nanometer or 60 nanometer film. So one has to also calibrate that part. While you are deciding, you may need to take a decision well in advance, but again that is a kind of optimization that one should go through. But in this case, the optimization may take less time because now you know what is the thickness. But if there is no thickness monitoring, the optimization may take more time. Okay, so that is the only advantage you may get with an real-time thickness monitoring. Now here the process of deposition is described schematically in brief. So generally we keep that instrument in a clean room. Then the major factors involved are the materials to be deposited, the available material and the substrate. So you have to decide what should be the substrate where you want to deposit the material, and you have to decide what should be the source material, right? And then you have to start the process. So this is a picture of a thermal deposition unit. This is the chamber where the deposition takes place. This is the control unit where you control your current, time, etc. You also can feed your recipe in this computer, and then the entire system will take care of it. So the instrument is not a very kind of benchtop system, it's a big system, and then one has to follow a process in order to deposit certain material on a substrate. So the first thing is you have to, for example, usually these chambers are kept in vacuum. So what we do is, say one process is complete, so that person while leaving will again put this entire chamber into vacuum and will leave it before going from this room or before he leaves. The purpose or the reason behind that is, if this chamber is not kept in vacuum, there will be air present. That air may create different contamination problem later. That's why once your process is done, they leave that chamber under vacuum. So initially the chamber remains under vacuum after the previous run, and then you have to vent that system. Venting that system meaning you have to put, say, nitrogen into the system in order to break this vacuum, because if it's vacuum you can't open this lid, the pressure is very less inside. So the process will start with venting, where you put, say, nitrogen, and then you create or vent or break the vacuum, you open the door, and then you put the substrate on top of this, and you also put the source material in the boat. So once you put the source material and the substrate, you again close the door, and once it is closed, again you vacuum the chamber, because vacuum is very important, otherwise again the gases or airs whatever is present may react with the system. So you vacuum it, and then you start heating this source material. Once you heat the source material, it will start evaporating. This evaporation will again get deposited on the substrate. Based on the thickness you need, you can decide the time, you can decide the current or the temperature of the board, and then once the deposition is done, again you have to vent, because without venting you can't open the door, the pressure is very high inside. We already have seen it's a high vacuum. So once you vent it, you open it, you take out the substrate, and then you take out the, if it's silicon, whatever it is. So it's like a substrate holder is present here. So you take out the holder first, and from there you take out the substrate, whatever you have put inside, and then you can do other processing with the substrate. You put the holder again back to the system, you close the door, again you vacuum it. So the purpose for the second vacuum is to make sure that there is no contamination present when the next person comes and start the process. That's why initially when you go to a thermal deposition or any deposition technique or any deposition system, you will find the chamber is kept under vacuum initially itself. So, that is the process what one has to follow in order to deposit certain material on a substrate. So, if you want to deposit say gold on top of something, you have to use gold as a source, and say if it is silicon, if you want to deposit gold on silicon, silicon will act as a substrate. Now, you may find that there are different materials that are not compatible. For example, if you want to deposit say material A on material B, so material B is the substrate, the adhesion between material A and B is not good. Even if you deposit, if the adhesion is not good, they will not be stable. After deposition, if you just touch or if you just put something on top of it, it will come out. So, that is not desirable. For that purpose, you may need an intermediate layer. For example, if you want to deposit gold on top of silicon, better if you put an chromium layer in the middle, so that adhesion is much better. So, in that case, you have to follow those processes and you have to create those recipes accordingly, so that you get a stable deposition or deposited layer on top of the substrate. So, there are different types of PVD techniques that we have seen. So, thermal deposition, EVM deposition, sputtering, these three are widely used PVD techniques. Then sputtering are also of various types. We have seen there are DC sputtering, there is RF sputtering, RF magnetron sputtering. So, sputtering is also of various types. And then based on application and fabrication requirement, one can decide the recipe. So, recipe is the process through which you will deposit say source material on top of the substrate. So, recipe will tell you what should be the current value, what should be the heat, what should be the vacuum, what should be the time for that deposition, so that you can get a certain thickness of material, source material on top of a substrate. So, in the upcoming discussion, we will discuss other deposition techniques. Till then, thank you.